This video shows a sleek industrial robot arm sweeping smoothly through a continuous arc on a factory floor. Generating flawless, ready-to-deploy code for a movement like this starts entirely in a virtual environment. Programming an industrial robot directly on the floor through manual trial and error is slow, wastes valuable production time, and risks crashing a heavy machine into expensive equipment. To build, test, and iterate robotic sequences without that physical risk, we use offline programming software like RoboDK. This layout shows the baseline hardware required to run the simulation seamlessly. You need a modern operating system, 4 GB of RAM, and a dedicated graphics card to handle 3D rendering. You also need the 3D files of your workpieces prepared in standard CAD formats like STL or STEP before opening the software. Taking a few minutes to verify your hardware and prepare your digital files up front is the only way to guarantee a frictionless physical deployment later. This mockup shows the software's initial, empty 3D workspace. We start by clicking the New Station menu to initialize a blank project. Next, we locate the prepared CAD models of our specific workpieces and import them directly into this empty station. This diagram illustrates how we must manually adjust these imported objects. We translate and rotate the parts precisely along their X, Y, and Z axes, so their digital placement perfectly matches your real-world layout. With the environment set, we access the internal software library to search for the exact brand and model of the physical robot being used. Once located, we download the chosen robot model and import it directly into the active digital workspace. We then position the base of the robot arm in precise spatial relation to the previously arranged workpieces. Creating an exact millimeter-perfect digital twin of the physical setup is the foundational step that ensures the final program will translate accurately to reality. Now we move to programming. We create a new program file and name it to reflect the specific mechanical task it controls. This diagram shows how we define the robot's physical movements. By clicking specific waypoints, we build a trajectory sequentially connecting multiple target nodes in 3D space. We then dictate the specific movement speed the robot must maintain as it travels between these established waypoints. We also insert wait commands into the sequence to pause the robot's movement for external physical processes, like allowing time for a welding delay. Next, we embed input and output instructions to trigger hardware changes, such as signaling the machine to swap out a robotic toolhead. Translating complex physical operations into a linear sequence of digital waypoints entirely removes human guesswork from robotic control. With the path built, we run an immediate test playback of the program trajectory to observe the sequence in action. This visualization shows a vector arm hitting a static block. Activating collision detection is mandatory. When flagged, we adjust the waypoints to route the path safely around the obstruction. The software then automatically smooths the trajectory, relaxing the path and minimizing cycle time. Now that the simulation is validated, the final procedural step is generating the robot-specific code file. This menu shows various manufacturer extensions. It is critical to select the exact file format that matches the manufacturer of your physical controller. Passing this rigorous virtual validation guarantees that the physical robot will perform at maximum efficiency without risking catastrophic damage. This illustration details the final physical process, transferring the finalized code file from the workstation directly to the robot's hardware controller via USB or local network. You can now execute the code immediately on the floor with full confidence that it is proven, efficient, and collision-free. As your processes scale, the software allows you to add secondary robots into the exact same virtual station. This video shows 2 robot arms moving in close proximity. This multi-robot setup allows engineers to design and test complex collaborative tasks between machines simultaneously. Mastering offline simulation shifts industrial automation from a process of high-risk physical trials to one of zero-risk digital certainty.